And we're live. Hello, everyone, and welcome to MAE 209. This is Probability and Statistics. My name is Richard Kohar, and thank you for coming to Tuesday's lecture, Lecture 17. And today's lecture is based on the normal distribution. Everyone can hear me okay on the audio. I'm just checking to make sure I'm not peaking. Everything good? Excellent. I think I have marked all the quizzes. So again, if you have questions about that, send me an email about that. I've also, if you have a question about kind of solutions or you're wondering what the answer was, I posted the solutions to quiz 2 just below the Moodle assignment for quiz 2, and you can see the solutions that way. Okay. So without further ado, here we go about the normal distribution. So I just have some general remarks before we start then. So the normal distribution is one of the most important distributions we'll probably study in this course. And the reason for that is because it can be applied to so many things in the real world. We find that things are normally distributed, and if they really aren't, they're pretty close, and so they're good enough that, again, we're using this as a model. It's a representation or an abstraction of what happens in the real world so that we can logically reason and make models about it and make conclusions from it. The other thing that you might hear me say is I'm so used to calling this a Gaussian distribution, and the reason for that is because it was first seriously studied by the German mathematician Carl Gauss, the one that you probably have encountered in engineering or scientific courses involving math. So some applications that are quite common for us to see is that people's heights can be normally distributed. We've seen things like their weight can also be normally distributed. Measurement errors, so we can measure something, but there's always going to be some variance away from it. So how far away do we expect it from the actual measurement? Reaction times in an experiment, things like calculating how quickly someone applies a brake or how quickly somebody can react to a situation involving in sports. Measures of intelligence have also been used. And many, many more. There's an article that came out in Biometrica, which is a mathematical journal that's focusing on statistics in Biometrica. Again, it was more of a journal for statistics being applied to biology. And that article had, in 1903, that was published by, I think it was Pearson, so many applications. It ran 60 pages. So why else is this useful for us? Even if we have like an individual trial or a sample or a person, while they might not be normally distributed, if you pool them together, and again, there's my disclaimer, my mathematical disclaimer, under suitable conditions, the overall distribution can be approximated using a normal curve. And this is what we'll call the central limit theorem, and I'll talk a little bit about this in this lecture, but really we'll talk about that in the next chapter. Okay, so I've amped up this distribution long enough. Let's start talking. Let's start drawing some of it. Let's actually see what it looks like. Okay. So a continuous random variable x is said to be normally distributed, and we have two parameters for it. Mu, which is what we're going to call the expected value, and sigma squared, that's the variance. And it's a continuous random variable x if it has the PDF or the probability density function given by the following. So we have our function f, and we have our value x, and we have our two parameters. So in this case, we'll have we'll have mu, which is our expected value, and the variance. The other notation that you'll commonly see too is that for kind of a shorthand in math, we'll write that x follows the normal distribution with some mu and variance. So we can write this as 1 over 2 pi sigma squared. And then we have e to the minus x minus mu, this is squared, all over 2 sigma squared. And that's for x on the reals, so the entire real line. And we also should have some parameter restriction. So we'll say that where mu can be between minus infinity and infinity, and the variance has to be positive. Or if you really were wanting me to keep it in similar form again, from 0 to infinity. So that is the PDF of the normal function, the normal distribution. And again, there's some, our usual suspects that we see. We have pi, and we also have a e. So again, that's e, which is the exponential function, or e is approximately 2.718. That's Euler's constant. So that's kind of important to remember. So now let's draw what that should look like. So here along the horizontal axis, I'll use x. And I'm going to use here, this will be mu. And it's going to look like a bell curve. Same thing. There. And right here, that's the point of inflection. Does anyone remember what a point of inflection means from our first year calculus course? What does that mean? That's right. It's transition from concave up to concave down, or vice versa. That's right. So again, in this case over here, this is switching from concave down to concave up, because again it's down, then it's switching to concave up. Similarly over here, oops, same thing over here. Oh, point of inflection, my bad. Point in inflection. Thank you. There should be an L, not inflection, but inflection. And over here, that's switching from concave up to concave down. So concave up to concave down. And as a refresher, how do you find the point of inflection? Yep, that's right, using the second derivative. So you find an x such that the second derivative should be, so if I use Leibniz notation, I'll use d squared of f Okay, so what's also nice about this is that, point of inflection is, I might be thinking of something else, but what I really was meaning to say was point of inflection. So what's also, why was I banging on about the point of inflection was, it also helps us to locate the distance from the expected value to where it hits the curve here. So when it hits at this point of inflection, that distance is equal to the standard deviation. So the other thing I was going to mention is, so we've done, here is the expected value, or some people will say mean. Over here is the standard deviation. What's something else that you notice about this curve? What property of the function can you see visually? Perhaps looking at what mu, it's symmetrical, yep. So this distribution is symmetrical. And what does that mean? Also, what does that imply? What else can I tell then about using the fact that I have a symmetrical distribution? What's another concept that we have done that you could figure out from this? Well, look at the area under the curve. With a symmetrical distribution, what's the area to the left of mu and what's the area to the right of mu? That's right. It should be 0.5 on both sides. That's right. And so what does that mean? %50 overall. Okay, yeah. And what did we learn from the previous lecture? What's important about, what was the concept that we used where the area was 50%? Percentile, yes, we were talking, we're getting really close to it. But what was special about the 50th percentile? What did we call that? The median, yes. So because we have a symmetrical distribution and it's symmetrical about the mean, that mu is equal to the median. So the expected value is equal to the median. Okay. So we have in probability theory that we have what's called the standard normal distribution. And that's where we have a random variable, and we'll call it z. It follows a normal distribution where it has 0 for the expected value and 1 for the variance. So that's mu, and over here is the variance. So that's what we call the standard normal distribution. So the PDF of this random variable z, just looking back to our formula for it, our PDF, what we do is we substitute our values of 0 and 1 into that. And so little z, 0 and 1. So we'll have it from so instead of sigma squared, it'll be just 1, so it's just 2 pi e to the minus. Now, in this case, mu is 0, so it's just x squared over 2. And if we need to compute this, then we use something like a less than or equal to z is less than or equal to b, and we integrate this from a to b. And that will give it our value that we want. Now, we can also do something like let's say z is less than little z, and maybe I should switch to just using a different, let's use a different z style. So what that would mean is this is going to be at 0. Here's kind of bell curve. And we get all that up to this point. So that's what I'm calculating right here. So z instead of x, yes. And the reason for that is because they use a special letter for this. So when we were talking about standard normal distributions, it's very common that they'll use the random variable z. Now, something like this so calculating the area under the curve is not possible analytically. Meaning that there's no closed form for this. We have to revert to using some sort of numerical integration. Now, you don't have to worry about using numerical integration, things like rectangles under the curve like we did with Riemann sums, because we use this so often that we have tables for this. Oh, sorry, I have an x in the... Oh, okay. Yes, I mean to have this as a z. Okay. So we have to use numerical integration, or we have to use a table. So Here's an example that we'll do. Let Z be a normally distributed random variable with an expected value of 0 and a variance of 1. Determine the following probabilities. So here is Z is less than or equal to 1.25. I'm going to switch to using just a thinner pen. So over here, I'm just going to draw what we're calculating. And so we need the area under the curve from 1.25. Okay, so in the back of the book, in one of the appendices, Appendix A, the third appendix inside of Section A, you have something like this. So notice that this is a standard normal curve. So this means that this is for 0, 1. And over here, they even give you a little bit of an illustration. So the probability of Z, it's all the area to the left of it. So the way that we read the table is that down the left-hand side gives us our first number and our first place in the decimal. And then on the top row is our second place decimal. So if I wanted something like negative 3.4, then I would just look at this value. If I wanted negative 3.41, well, then I need to go to this decimal, 0.01, and look here, so on and so forth. So when I need to look at this value, 1.25, I go to the positive one, 1.25, and I look down this row, 1.2, so there's 1.2, I need 0.5. Okay, so this is what I need. This is the value. So it's 0.8944. So that's what I can write down. Okay. For part B, it's asking us what's the probability of Z greater than 1.25. So how do I calculate this? And remember what it means visually. What this is asking for is the area to the right of this. So what do you think in the chat? How could I calculate that? Because I remember this paper or this table is set up for the area to the left of the curve. Yep, 1 minus the previous answer. So you can do 1 minus C less than 1.25. And that equals 0.1056. Now here's another one. We have the probability of z less than or equal to negative 1.25. So we can look at the table here, and negative 1.25. So that gets us right here 0.1056. Now, why is this value the same as what we calculated in part B? Yes, it's symmetrical. That's right. It's because it's symmetric. Good. Then what about if the probability of z is greater than negative 0.25? What do you think it is in the chat as I kind of illustrate this using a... Mm-hmm. Yep. Okay, and lastly, we need to calculate the probability that z is between minus 0.38 and 1.25. So the way that we're going to do this is we're going to do it how we had learned in the previous lecture, which is we're going to find the CDF up to 1.25. So it's the probability that z is less than or equal to 1.25 minus, and same thing up to this point, oh, did I miss something? Okay. Sorry, I don't know what happened in the chat. So we've already calculated what that value is. Bot, okay. So we'll use what we had calculated, which was 0.8 0.94. And then we'll subtract it for that value of negative 0.38. So same thing, we'll look down this table. So down here, and we'll go to 8. So right here is 0.3520. And so that gives us our final value of 0.5424. So what happens when we have non-standard? Normal distributions, meaning that it's not a distribution that has an expected value of 0 and the variance of 1. So what we do is we transform them to a standard normal distribution. And the reason for that is so that we can use the tables that we have already. So the way that we transform that is, we'll say that if x has some normal distribution with the expected value of mu and a standard, or well, a variance of sigma squared, then we can actually transform it to have it z is equal to, we use our random variable x minus mu over sigma. And in this case then, that z would have a normal distribution, the standard normal. So what does that mean in terms of when we're applying to our probabilities? Well, if I am thinking between A and B for that random variable x, I just apply that transformation to it. So at the heart of it is going to be z, and we need to figure out what the values of a and b would be. So we're transforming from a to something that would bound now this standard normal variable. So we're going to use a, so that's our x value. So a minus mu over sigma, And then over on this side, it's b, so that's our value. So b minus mu over sigma. They also use and then similarly we can do the same thing. We have for like x is less than a, well, that's equal to our standard variable, our standard normal, being a minus mu over sigma. If we have it as x is greater than b, well, that is 1 minus the probability of x less than b. And transforming it, I can have it as z is less than b minus mu over sigma. So those are our important formulas. Okay. So let's do an example. I have 5 minutes left. So here's an example. We'll use it from intelligence. So IQ in particular, in a particular population, is measured by a standard test, and we know this to be approximately normally distributed. So when we do IQ tests, it's on a population. This is what we usually expect. Here's my normal distribution. What we expect is that mu is equal to 100, and that the standard deviation is 15. So that means that we'll let x be some person that we randomly select from that. And that'll have a normal distribution of 100 and a variance of 15 squared. So for part A, what is the probability that a randomly selected person has an IQ above, let's do 130. Well, what we're asking for then is what's the probability that x is greater than 130, which we can think of that as the complement, 1 minus x less than or equal to 130. And we don't have a table for this probability distribution, so we can convert this to a standard normal distribution. So we'll switch to z in this case. So this is our value that we want. So it's 130 minus 100 over 15. So what you get then, make sure I do this correct. So that should be 30 over 15, right? Should be 2. So now we go to our lookup table. We need to look up 2 and just 2.0. And then in this case, it's 0.9772. And then we take 1 minus 0.9772, which gives us 0.0228. And if you want to think about that as in terms of percentage, it's approximately 2.3% chance. Okay. So as an exercise, what I would like you to do is find the probability that a person, again randomly selected, has an IQ within 1 standard deviation. From the mean. From the mean, or the expected value. Okay. So I'll leave that as an exercise. Is there any questions before we finish for today? Yes, questions will be posted. I'll do that by today. Okay. Well, thank you everyone for tuning in. If you have any questions, feel free to send me an email at my RMC account. Otherwise, enjoy the rest of your day. Take care.